This is Chapter 10, Generators. Objectives for this chapter: explain how mechanical energy can produce electrical energy, state Lenz Law, discuss the difference between direct current and alternating current, explain the construction of a function of a generator, list 3 types of generator losses, identify the types of generators, discuss voltage and current regulation, calculate average and effective values of AC signals, explain and deconstruction of a oscilloscope, determine voltage using an oscilloscope display, determine frequency using an oscilloscope display. Some of the keywords and terms used in this chapter are amplitude, average value, cathode ray tube or CRT, cycle, eddy current, effective value, frequency, generator, Hertz or Hz, instantaneous polarity, Lenz Law, magnetic conduction, oscilloscope, peak, period, phase displacement, regulation, Rms value, sine wave, and vector. 10.1 Electrical energy from mechanical energy. In Chapter 9, the discoveries of Hans Christian Ørsted were cited as proof that electric current produces a magnetic field. In 1831, scientist Michael Faraday wondered if electricity produces magnetism, then can magnetism produce electricity? Magnetic conduction. Based on his research, Faraday learned that magnetism could in fact produce electricity. He found that a moving conductor through a magnetic field induced or brought about a voltage in the conductor. This is known as magnetic induction. 3 things are required to induce a voltage. There must be a magnetic field, a conductor, relative motion between the field and the conductor. For this, see figure 10-1. In the following experiment, you can watch the principles of magnetic induction at work. Refer to figure 10-2. A coil is attached to a galvanometer. A galvanometer is a meter that measures the size and direction of a small electric currents. A permanent bar magnet is placed in the hollow coil. As the magnet moves into the coil, the needle on the meter shows current flowing in one direction. As the magnet is taken out of the coil, the needle shows current flowing in the other direction. When the magnet is still, no current is produced. The same movements are produced when the magnet is held still and the coil is moved over the magnet. Figure 10-3 shows the action of a coil turning in a magnetic field. In position A, the coil top moves parallel to the field of magnetism. No voltage is produced. In position B, both sides of the coil are cutting the field at right angles. The highest voltage is produced at this right angle. In position C, it's like position A, the voltage drops to 0. In position D, the coil is again cutting the field at right angles, where the highest voltage is induced. However, in position D, the voltage is in the opposite direction of that produced in position B. The curve in 10-3 shows the voltage induced in one turn of the coil. How is this induced voltage created? Figure 10-4 shows single conductors passing through a magnetic field. At the top, the conductor is pushed downward through the magnetic field. On the bottom, the conductor is pushed back upward. The current generated is shown by the arrows. In each case, the induced current in the conductor forms a magnetic field around the conductor. The field around the conductor opposes and is repelled by the fixed field. This phenomenon is stated in Lenz Law. The polarity of an induced electromagnetic force is such that it produces a current. The magnetic field of this current always opposes the change in the existing magnetic field. More simply said, Lenz Law states that the field induced around the conductor is opposed by the existing field. Therefore, in order to produce electricity, some form of mechanical force must be applied to overcome this opposition and turn the coils. For example, water and steam supply the mechanical energy or force to turn turbines in large power plants. The strength of the induced voltage in a rotating coil depends on two things: the number of magnetic lines of force cut by the coil, and the speed at which the conductor moves through the field. When a single conductor cuts across 1 million or 100 million or 10 to the 8th magnetic lines in 1 second, 1 volt of electrical pressure is produced. This voltage can be increased by winding the armature with many turns of wire, by increasing its speed of rotation, or both. Reviewing what was learned in Chapter 6, this link can be expressed by the mathematical equation shown, where E equals induced voltage, where phi equals the lines of magnetic flux, and N equals revolutions per second. For example, if a fixed magnetic field consists of 10 to the 6th lines of magnetic flux, and a single conductor cuts across the field 50 times per second, the induced voltage would be equal to the formula shown on the screen, which gives you 1/2 volt produced by this generator. DC versus AC. DC current, or direct current, flows in only one direction through a conductor. If the flow of electrons is constant, it is called pure direct current. If the flow is intermittent, it is known as pulsating DC, or pulsating direct current. See figure 10-5. Alternating current flows in alternating directions back and forth through a conductor within a given time period. Alternating current is shown at the bottom of figure 10-3 from before. This curve is called a sine wave. Construction of a generator. A generator is a device that changes mechanical energy into electrical energy. You saw this change in figure 10-3 from before. The revolution of the coil, mechanical energy, was changed to induced current, electrical energy. This action is an example of a very simple generator. The electricity produced in this simple generator is not very useful because it is not powerful enough to do much work. The system requires some improvements. A stronger magnetic field or magnetic field can be created for this improved generator by replacing the permanent magnets with electromagnets. Field coils can be replaced over pole pieces or shoes that are fastened to the steel frame or generator case. The revolving coil or armature is suspended in the case, resting on proper bearings. The single coil is replaced by wire coils of many turns on the armature. The rotating armature is connected to the outside circuit through commutators or slip rings. The commutators and slip rings touch brushes in the outside circuit. Generator brushes are constructed mainly of simple soft carbon. The major difference between an AC generator and a DC generator is the use of slip rings in the AC generator and the use of a commutator split ring in the DC generator. Both slip rings and split rings provide the electrical current connections from the armature to the generator load circuit. Two slip rings are used on AC generators. The slip rings provide a mechanical means of maintaining the connection between the armature circuit and the outside circuit. See figure 10-6 for this. In the AC generator, the slip rings are in constant contact with the brushes. Since an alternating current is produced in the armature circuit, the outside circuit is also AC. Both the DC generator and AC generator produce an AC current in the armature windings. When DC is desired in the outside circuit, a set of commutator segments and a set of brushes are used. A commutator or split ring is a device that reverses the electrical connections and is used on DC generators. See figure 10-7. The mechanical connection between the outside circuit and the armature constantly changes because of the brush and commutator connections. The action of the commutator and brushes maintains a constant flow in one direction toward the outside circuit. For this, see figure 10-8. Study this figure closely to see how the direction of the current is maintained in the outside circuit or load circuit. The drawings show the action of the commutator and brushes. The polarity of the brushes is constant. The polarity of the slip rings in the AC generator, figure 10-6, changes as the direction of the current changed with each half revolution. In the DC generator, however, the alternating current in the armature is changed to a pulsating direct current. Note that the current in the outside circuit of the DC generator always flows in one direction. The output of the generator is shown in figure 10-9. The voltage rises and falls from 0 to a maximum to 0, but always in the same direction. Follow the action in figure 10-8, the figure from before. Rewind if needed. Brush A is in contact with commutator section A, and brush B is in contact with commutator section B. The first induced wave of current flows through the armature out of brush B, around the external circuit into brush A, completing the circuit. When the armature revolves 1/2 turn, the induced current will reverse its direction. However, the commutator sections have also turned with the armature. The induced current flowing out of commutator section A is now in contact with brush B. This current flows through the external circuit to brush A into commutator section B, completing the circuit. The current flows through the external circuit in the same direction both times. The commutator has acted as a switch. It reverses the connection to the rotating coil when the direction of the induced current was reversed. The current in the outside circuit is pulsating direct current. The output of this generator is not smooth direct current. The weakness of pulsating DC can be improved in two ways. The number of rotating coils on the armature can be increased, and the commutator sections can be supplied for each set of coils. To help you understand how the coils are added to the armature, examine figure 10-10. Each coil has its own induced current. As the current starts to fall off on one coil, it is replaced by an induced current in the next coil. The current is created as the coils cut across the magnetic field. A graph of the output from the generator in figure 10-10 is shown. Generator losses. All of the mechanical power used to turn the generator is not converted into useful electrical power. There are some losses. I-squared losses. You will recall that all wires have some kind of resistance. The size of this resistance depends on the wire size, material, and length. Resistance uses power. In the generator coils, there are many feet of copper wire. The resistance of this wire must be overcome by the induced voltage. Voltage used in this manner supplies nothing to the external circuit. It only creates the heat in the generator windings. Power loss in any resistance is equal to P equals I squared times R, or current squared times resistance. Of special concern is the fact that power loss increases by the square of the current. To be specific, if the current of the generator doubles, the power loss is 4 times more. The limiting factor in generator power is usually the wire size and current capacity of the armature windings. Losses resulting from resistance in the windings are called copper losses, or I squared R losses. Eddy currents. The armature windings in the generator are wound on an iron core, which is slotted to hold the coils. Like a conductor, as the solid iron core rotates, it induces voltages, causing an alternating current to flow in the core. This alternating current is known as an eddy current. It produces heat, which is a loss of energy. To reduce this loss, cores are made of built-up thin sections of laminations. Figure 10-12 shows this. Each section is insulated from the next section by lacquer, or at times only oxide and rust. These laminations reduce the voltage in the core and increase resistance to the power draining eddy current. Eddy currents increase in the core as the speed of the rotation increases or the field density increases. When iron cores are used in rotating machines and transformers, they are laminated to reduce eddy current losses. Hysteresis. The third loss occurring in a generator is called hysteresis loss. Hysteresis is also called molecular friction. As the armature rotates in the fixed magnetic field, many of the magnetic particles in the armature core remain lined up with the fixed field. These particles then rotate against those not lined up in the field. This rotation causes internal friction between the magnetic particles and creates a heat loss. Generator manufacturers use a silicon steel which has a low hysteresis loss, annihilating the core heat process further reduces this loss. Annihilating the core, a heat process further reduces this loss. Time to review questions for section 10.1. Number 1, voltage is the highest when the armature coil moves perpendicular, parallel, at right angles to the magnetic pole. And that was the answer, perpendicular. Question 2, in your own words, explain Lenz Law. It is a field induced into a conductor which repels the conductor's own field. 3, what major factors determine the strength of induced voltage? Field strength, or amperage, the speed of the coil, the Number 4, define current and alternating current. Draw a wave pattern for each and label positive, 0, and negative voltage peaks. And you can see that on your screen towards the bottom, middle. Question 5. A blank is used to maintain a constant direction of current from the armature. And the answer is a commutator. It's used to maintain a constant direction of current from the armature. Question 6. Describe the difference between slip rings and split rings. The difference is that slip rings allow the current to change direction as an AC current, while the split rings don't. They allow for only one direction of current. Sketch a DC generator. Use arrows to show the current. And as you can see, I have tried to do that in the middle of the screen towards the bottom again. A DC generator has a split ring, meaning that it's a commutator that has two isolated or separate sides, but they are in one unit, usually a cylinder. That's what allows the change in polarity of the slip ring and the coils, and also allows for the same polarity or same current direction to remain at the brushes or the outside circuit. Number 8. Name 3 types of generator losses. First one is eddy current. The second one is copper loss or I2R loss. And the third one is hysteresis or hysteresis loss or hysteresis molecular loss. Point 2, types of generators. There are a number of different types of generators. Several of these generator types will be discussed briefly. Study their similarities as well as their differences. Generators can be distinguished by their method of excitation. Self-excited generators can be separated further into categories such as shunt, series, and compound. One feature that separates generators is the excitation method, the method that is used to start the generator running. Some generators require a separate power source during the starting of the generator. These are called separately excited field generators. Other generators use the generator's own leftover magnetism in place of that power source. These are self-excited generators. Separately excited field generator. The generator output is determined by the strength of the magnetic field and the speed of the rotation. The field strength is measured in ampere turns. So an increase in currents in the field windings will increase the field strength. Output voltage is in direct proportion to the field strength times the speed of rotation. Therefore, most output regulating devices depend on varying the currents in the field. The field windings can be connected to a separate or independent source of DC voltage. See figure 10-13. This is the separately excited field generator. With the speed constant, the output may be varied by controlling the exciting voltage of the DC source. This is done by inserting resistance in the series with the source and field windings. The self-excited generator. A self-excited generator uses no separate source of voltage to excite the generator field winding. The self-excited generator produces a small voltage when the armature windings cut across a weak magnetic field. This weak magnetic field is caused by magnetism left over in the pole shoes or field coil cores after the voltage and current have ceased to flow. The magnetism left in a magnet after a magnetizing force has been removed is called residual magnetism. Residual magnetism was first discussed in Chapter 9. Look ahead to the diagram of the shunt generator shown in Figure 10-14. A residual magnet field will cause a small voltage to be produced as the armature conductors rotate past the field poles. The small voltage produced will in turn cause the current to increase through the field poles. An increase in the field pole magnetism will cause a further increase in output voltage. The relationship of the current produced by the armature directly increases the amount of magnetism in the field poles. And this is how the self-excited generator works. The magnetism produced by the armature voltage will increase until the field poles reach saturation, the point where the poles cannot contain any more magnetic lines of force. A shunt generator. The shunt generator derives its names from the way the field pole coils are connected in parallel to the armature. See Figure 10-14. Another way of saying parallel is the term shunt. The field windings consist of many turns of small wire. They use only a small part of the generated current to produce the magnetic field in the pole's windings. The total current generated must, of course, be the sum of the field excitation current and the current delivered to the load. Thus, the output current can be thought of as varying according to the applied load. The field flux does not vary to a great extent. Therefore, the terminal voltage remains constant under varying load conditions. This type of generator is considered a constant voltage machine. All machines are designed to do a certain amount of work. If overloaded, their lives are shortened. As with any machine, the life of a generator can be shortened by an overload condition. When overloaded, the shunt generator terminal voltage drops rapidly. Excessive current causes the armature windings to heat up. The heat can cause the generator to fail by destroying the thin coat of insulation covering the armature wires. Series generator. The series generator is so named because its field windings are wired in series with the armature and the load. Such a generator, series generator, is sketched in Figure 10-15. A series winding by itself will provide a fluctuating voltage to the generator load. As the current increases or decreases through the load, the voltage at the generator output terminals will greatly increase or decrease. Because of the wide difference in output voltage, it is not a very practical generator to use if the load varies. The compound generator. The compound generator uses both series and shunt windings in the field. The wire size of the series winding is usually the same size as the armature conductors. These windings must carry the same amount of current as the armature since they are in series with each other. The series windings are mounted on the same poles with the shunt windings. Both windings add to the field strength of the generator field poles. If both act in the same direction or polarity, an increase in load causes the increase of current in the series coils. This increase in current would increase the magnetic field and the terminal voltage of the output. The fields are said to be additive. The resulting field would be the sum of both coils. However, the current through the series windings or the series winding can produce magnetic saturation of the core. This saturation results in a decrease of voltage as the load increases. The way terminal voltage behaves depends on the degree of compounding. A compound generator that maintains the same voltage either at no load or full load conditions is said to be flat compounded generator. A over compounded generator then will increase the output voltage at full load. An under compounded generator will have a decreased voltage at full load current. A variable load be placed in parallel with the series winding to adjust the degree of compounding. Figure 10-16 shows schematic diagrams of the shunt, the series, and the compound generator. Voltage and current regulation. The regulation of a power source, whether a generator or a power supply, can be defined as the percentage of voltage drop between no load and full load. So mathematically it can be expressed as the formula shown on the screen. To explain this formula, assume that the voltage of a generator with no load applied is 100 volts. Under full load, the voltage drops 97 volts. Filling in the equation is shown at the bottom of your screen. In most uses, the output of the generator should be maintained at a fixed voltage value under varying load conditions. The output voltage of the generator depends upon the field strength. The field strength depends upon the field current. Current, according to Ohm's law, varies inversely with resistance. Therefore, a device that would vary the resistance in the field circuit would also vary the voltage output of the generator. This regulator is shown in figure 17. It was often used in automobiles. The generator output at terminal G is joined to the battery and the winding of a magnetic relay. The voltage produced by the generator causes a current to flow in the relay coil. If the voltage exceeds a preset value, the increased current provides enough magnetism to open the relay contacts. Notice that the generator field is grounded through these contacts. When they open, the field current must pass through the resistance R to ground. This resistance reduces the current, which produces the field strength and produces the terminal voltage. When the terminal voltage is reduced, the relay contact closes, permitting maximum field current. The terminal voltage rises. In operation, these contact points vibrate. They alternately cut resistance in and out of the field circuit and maintain a constant voltage output of the generator. Mechanical magnetic relays have served this purpose for many years. Now, however, electronic devices are being used on cars. An electronic regulator using an integrated circuit for the switching function is shown in figure 10-18. A study of integrated circuits is found in chapter 19 of this text. Section 10.2. Number 1, generator output is determined by 2 items. Name these items: field strength and resistance. Number 2, this generator requires an external power source to provide voltage to the field windings. A, series generator, B, compound generator, C, shunt generator, or D, separately excited field generator. Correct answer is D. This generator is considered a constant voltage device. A series generator, B, a compound generator, C, a shunt generator, and D, a separately excited field generator. The correct answer is B. 4. This generator has both series and shunt windings in the field. A, series generator, B, compound generator, C, shunt generator, D, separately excited field generator. Correct answer is B. 5. State the mathematical equation for regulation of a power source. That would be voltage no load minus voltage full load divided by voltage full load, all that multiplied by 100 equals your percentage regulation. .3 Alternating current. Direct current flows in only one direction. Alternating current changes its direction of flow at times in the circuit. In DC, the source voltage does not change its polarity. In AC, the source voltage changes its polarity between positive and negative. Figure 10-19 shows the magnitude and polarity of an AC voltage starting at 0. The voltage rises to maximum in the positive direction. It then falls back to 0. Then it rises to maximum in the opposite polarity and returns to 0. The current wave is also plotted on the graph. It shows the flow of current in the direction of the flow. Above the 0 line, current is flowing in one direction. Below the 0 line, the current is flowing in the opposite direction. The graph in figure 10-19 represents instantaneous current and voltage at any point in the cycle. But what is a cycle? A cycle is a sequence or chain of events occurring at in a period of time. An AC cycle can be described as a complete set of positive and negative values for AC. The alternating current in your home changes direction 120 times per second. It has a frequency of 60 cycles per second, or 60 CPS. Frequency, measured in cycles per second, or hertz, is the number of complete cycles occurring in 1 second. If 60 cycles occur in 1 second, then the time period for one cycle is 1/160th of a second, or 0.0166. This period of the cycle, refer again to figure 10-19, the maximum rise of the waveform shows the amplitude of the wave, including the peak, highest point, voltage, and current. We learned that induced current in a rotating wire in a magnetic field flowed first in one direction and then in the other direction. This was defined as alternating current. The points to remember are the frequency of this cycle of events increases as rotational speed increases. The amplitude of the induced voltage depends on the strength of the magnetic field. Vectors. When solving problems involving alternating currents, vectors are used to depict the magnitude and direction of a force. A vector is a straight line drawn onto a scale that represents units of force. An arrowhead on the line shows the direction of the force. The length of the vector shows the magnitude. The development of an AC wave is shown in figure 10-20. This wave is from a single coil armature, represented by the rotating vector making one revolution through a magnetic field. Assume that the peak induced voltage is 10 volts. Using a scale in which 1 inch equals 5 volts, the vector is 2 inches, or 10 volts long. Vectors of this nature are assumed to rotate in a counterclockwise direction. The time base in figure 10-20 is a line using any convenient scale. It shows the period of one cycle or one revolution of the vector. The time base is grouped into segments that represent the time for certain degrees of rotation during the cycle. For example, at 90 degrees rotation, 1/4 of the time period is used. At 270 degrees rotation, 3/4 of the time period is used. The wave is developed by plotting voltage amplitude at any instant of revolution against the time segment. The developed wave is called a sine wave. The instantaneous induced voltages are proportioned to the sine of the angle theta that the vector makes with the horizontal. Refer to the appendix for explanation of trigonometric functions and tables. The instantaneous voltage may be found at any point in the cycle by making use of the following equation. E equals E max times sine theta. Notice that the lowercase e was used to represent the instantaneous voltage instead of the usual uppercase. By convention, instantaneous values are represented with lowercase variables. To apply this equation, assume that an AC generator is producing a peak voltage of 100 volts. What is this instantaneous voltage at 45 degrees of rotation? For this, follow the formula given, where E equals 100 volts times sine 45 degrees, which equals to 100 volts times 0.707, which is 70.7 volts. Average and effective values. A study of the differences between the AC and a direct current raises a key question. What is the actual value of the AC wave? The voltage and current vary constantly to reach peak value only twice during a cycle. Often the average value of the wave is needed. The average value is the mathematical average of all of the instantaneous values during one half cycle of the alternating current. The formulas for computing the average value from the peak value max of any AC wave are shown. If E average or I average is known, the conversion to find E max or I max can be made using the equations shown at the bottom. A more useful alternating current value is the effective value. The term effective value comes from scientists finding the AC heating effect equivalent of a direct current. A specified volume of water was heated using a specified voltage level of DC, then the same quantity of water was heated using AC. The AC voltage that produced equivalent heating to the DC voltage was the effective value. Formulas to find the effective value of any AC voltage or current are shown on the screen, where Emax and Imax are the peak values of the AC signal. If E effective or I effective are known, the conversion to find the peak values can be made using the equations at the bottom of your screen. The effective value is also named the RMS value, or root mean square value. It gets its name because the value represents the square root of the average of all currents squared between 0 and maximum of the wave. The currents are squared so the power produced can be compared to direct current. Watt's law states that power equals current squared times resistance. Using the 0.707 factor, the value of a direct current can be found that will equal the alternating current. For example, a peak AC current of 5 amperes produces the same heating effect as a resistance as a DC current of 3.53 amperes. Plugging in the formula, current effective equals to 0.707 times 5 amperes of AC, in this case, gives you 3.53 amperes DC. Note that the average and effective values can be applied to either voltage or current waves. Phase displacement. A few waveforms have been drawn on the same time base to show the phase relationship between them. For example, in figure 10-21, waveforms E and I show the voltage and current in a given circuit. The current and voltage rise. The current and voltage rise and fall at the same time. They cross the zero line at the same point. The current and voltage are in phase. The in-phase condition only exists in the purely resistive circuit. More will be discussed on this topic later. Many times the current will lead or lag the voltage, figure 10-22. When the current wave leads or lags the voltage wave, the two waves are said to be out of phase. This creates a phase displacement between the two waves. Displacement is measured in degrees. The phase displacement is equal to the angle theta between the two polar vectors. The alternating current generator. The AC generator is like the DC generator in many respects, with one key exception. The commutator is omitted. The ends of the armature coils are extended out to slip rings. Brushes sliding on the tip or on the slip rings provide connection to the coils at all times. The current in the externally connected circuit is an alternating current. In large commercial generators, the magnetic field is rotated and the armature windings are placed in slots in the stationary frame or stator of the generator. This method allows for the generation of large currents in the armature while avoiding sending these currents through moving or sliding rings and brushes. The rotating field is excited through slip rings and brushes by a small DC generator mounted on the same shaft as the rotating magnetic field. This small DC generator is called an exciter. The DC voltage is needed for the magnetic field. Commercial power generators convert many different items, such as moving water, coal, oil, wind, nuclear energy, into electricity. The force mechanism that is used to turn the generator is called the prime mover, figure 10-23. The alternator. The AC generator, also called an alternator, is used in the charging system of all US automobiles. Figure 10-24 shows the inside of the unit, including a built-in voltage regulator to control output. The output is rectified from alternating current to direct current for charging the battery and other electrical devices in the car. Manufacturers say the alternator has some advantages over the DC generator. These advantages include higher output at lower speeds, as well as trouble-free service. And now questions for review for section 10.3. Number 1, define alternating current cycle. It is a changing waveform during a second that alternates positive to negative. Number 2, fill in the blank. The blank is the number of cycles per second. That is frequency. Number 3, what is a vector? It is magnitude and direction. Number 4, if the effective is 1.75 volts the maximum voltage is, following the formula shown, is Emax equals to 1.414 times E efficient, which equals to 1.414 times 1.75 volts, which equals to 2.47 volts. Number 5, another name for effective voltage is root mean square, or RMS. Number 6, explain the terms in phase and out of phase. In phase is when the current or voltage in an electrical waveform match both polarity and timing of the peaks, valleys, and the zero measurement. Out of phase is just the opposite. The current, voltage, and the electrical waveform do not match the polarity and timing of the peaks, valleys, and the zero measurement. Three-phase generators. The most common generator used in production for electric power is the three-phase generator. It consists of a rotating magnetic field inside 3 sets of windings. For this, see figure 10-25 on your screen, part A. The 3 sets of windings are referred to as the armature of the generator. As discussed earlier, the armature provides power for the load circuit. In this case, the generator has a stationary armature and a rotating magnetic field. See figure 10-25 again, part B. Understanding how three-phase generator power is developed will be of great help when developing an understanding of AC motors in chapter 13. Look again at figure 10-25, part A. The sine wave that develops from three-phase electrical systems is unique. The three-phase windings of the armature are connected as pairs. They are called phase A, phase B, and phase C. As the magnetic field rotates inside of the generator armature windings, 3 different sine waves develop. The 3 waves are 120 degrees or electrical degrees apart. See figure 10-25, part C. It is important to note that each of the 3 phases develops the same frequency and same peak voltage. The difference between the 3 phases is that each phase develops positive and negative voltage peaks at different times, making each phase unique. The coils of the three-phase generator can be connected in series or parallel. When connected in series, it is called a delta connection. When connected in parallel, it is called a Y or star connection. The reasons for their names can be seen in figure 10-26. You may have heard of terms 120/240 volt and 120/208 volt and wondered which is correct. Both terms are correct. In fact, the voltage present is determined by the type of generator connection used. A Y connection provides 120/208 volts, and delta connection provides 240 volts with no common or neutral connection. Delta is used mainly for heavy industrial work or loads, while the Y connection is used to support both power and lighting circuits. The delta and Y connections are covered in detail in chapter 12. While some equipment will operate on either voltage, it is best to connect a piece of machinery to the voltage level specified in its operator's manual. Parallel generators. Large generator plant systems must provide millions of watts of power. Consists of several generators connected in parallel. When generators are connected in parallel, three electrical characteristics of each generator must match. These characteristics are the generator's frequency, voltage, and instantaneous polarity. If all three items do not match and the switch is closed to connect the two generators, an electrical fire and explosion are likely to occur. If the voltages of two parallel generators do not match, they can be made to match by adjusting one of the field pole rheostats. A slightly trickier part of parallel generators is matching the correct frequencies of the two generators. The frequency or hertz of each generator can be compared using a frequency meter. If the frequencies do not match, we need to speed up or slow down one of the generators until they match. Figure 10-27 shows sine waves of matching and non-matching instantaneous polarity. Each generator is producing a 120 volt output at 60 Hz. However, in the waves shown on the top, the third requirement, instantaneous polarity, does not match. The two sine waves in the figures are slightly off. Notice how their peaks do not align on the time axis. The instantaneous polarities of the AC generators refer to that part of the sine wave that is represented at the output terminals of each generator at that instant of time. These outputs could both be positive or one positive and one negative. Ideally, if both sine waves patterns match, the generators have identical instantaneous polarity. These generators can be connected together electrically. A simple way to tell if two three-phase generator outputs match is called the two dark, one light method. Two lights are connected across the phase A and B outputs of both generators in such a way that they match in polarity, voltage, and frequency. Both lamps should not light, since there would be no difference in potential across the lamps. Another lamp is connected across the two out-of-phase phases of the generator. This lamp should light, indicating that the two phases are out of phase with each other. For this, see figure 10-28. Again, the two dark, one light method of parallel generators. The two lamps connected across in-phase lines from the two generators remain dark. The third lamp is connected across two out-of-phase lines. This lamp will glow. These two generators can be connected in parallel safely. Troubleshooting generators. Generators generally fail due to one of three things: excessive brush wear, excessive bearing wear, and electrical overload. Excessive brush wear: as the brushes wear down, more arcing is produced between the brushes and the commutator. Segments or slip rings. Excessive wear will damage the surface of either the commutator segments or the slip rings. A bluish burn pattern will be evident. Excessive brush wear can be determined by physical inspection. The measurement for minimum brush length for a generator can be found in the owner's manual. The brushes should be replaced in excessive wear. If excessive wear is found, brushes should be dressed when being replaced. Dressing brushes refers to shaping the end of the brush to match the surface of the commutator or slip ring. A fine grade or sandpaper or emery cloth can be used for this purpose. The sandpaper is placed between the brush and the commutator with the rough side facing the brush. Rotating the commutator causes the end of the brush to wear down to match the shape of the surface it is writing against. For these, see figure 10-29. Excessive bearing wear. Worn bearings will cause a roaring sound. Excessive vibration can also be present. Another sign of excessive bearing wear is a shiny spot appearing on the armature. This spot is caused by the armature rubbing against a pole piece as the bearing wears out. Bearings should be lubricated on a regular schedule and indicated on the owner's manual. More bearings are permanently sealed and require no lubrication. Some bearings. If bushes and end bearings are properly maintained, and an electrical generator can easily provide more than 20 years of service. Electrical overload. Another cause of failure is electrical overload. Electrical overload causes the electrical insulation to break down, resulting in a short circuit or ground condition. Most times the damage can be detected by the naked eye. A dark discoloration is a sign of excessive overload of a conductor. Test instruments are needed to determine if the armature or field windings are good or bad. Usually a voltage equal to the generator voltage is used to check the windings for grounds. Most multimeters only use a 9-volt battery and cannot detect a ground created when 120 or 240 volts are present during generator operation. Heat from an excessive overload can also cause the generator pole pieces to lose their residual magnetism. This is very damaging to the self-excited generator. If the residual magnetism is lost, the generator will fail to build up sufficient voltage. Residual magnetism can be restored by connecting a separate DC power supply, such as a battery, to the field windings. Lesson on safety. Before connecting the separate DC power supply to the field windings, the armature leads must be disconnected to prevent the generator from rotating. When the voltage is applied to a generator, it will revolve as a motor. Review questions for section 10.4. Describe in your own words what is meant by three-phase power. Three-phase power is three separate and distinct voltage and currents waveforms which are generated by a delta or Y coil configuration generator. Number 2, a delta connected generator has its windings connected in series or parallel. The answer is in series. Question 3, if a three-phase power generator supplied 120/208 volts, would it most likely be from a delta or Y connection generator? The correct answer is a Y configuration. Delta configuration is usually a 120/240 volt, which doesn't require a neutral or a ground wire. What three characteristics must match before you can connect two generators in parallel? Frequency, voltage, and instantaneous polarity. Those are the three characteristics that must match. Number 5, what are the three major causes of generator failure? Excessive brush wear, bearing wear, and electrical overload. How may a self-excited generator lose its residual magnetism? From heat, from excessive overload. 10.5, the oscilloscope. The oscilloscope is a test instrument that permits observation of waveform patterns representing voltages in an electronic circuit. Figure 10-30. It is a priceless service instrument. At first, the oscilloscope can appear to be a very complex instrument, but after a little familiarization, you will see that it is really very easy to use. All oscilloscopes have very similar features, but there is some degree of variation among different models. The basic principles and operating controls covered in this unit will be the same for most oscilloscopes. Oscilloscopes display waveforms on a cathode ray tube or CRT. An electron beam is emitted from the cathode gun in the CRT tube. The beam travels between the two sets of beam deflector plates. One deflector plate is for horizontal deflection of the electron beam, and the other plate is for vertical deflection. The electron beam strikes the inside of the surface of the CRT display. This surface is coated with a luminous material such as phosphorus. When the luminous display screen is struck by the electron beam, it produces light. The light leaves the pattern on the display screen that represents the amplitude or height and time period width of the electrical wave being observed and studied. See figure 10-31. If an AC voltage is applied to the scope, the vertical deflection circuit controls the vertical deflection plate magnetic intensity. The vertical plate causes the beam of electrons to produce a wave of light on the display screen that is similar to the amplitude of the input voltage. This wave represents the instantaneous voltages during the cycles of an AC input. The horizontal sweep oscillator can be adjusted through a wide range of frequencies until it matches the frequency of the input voltage. Once the horizontal sweep is matched appropriately to the input voltage frequency, a series of light waves with a width that graphically represents the frequency of the input voltage is displayed on the CRT screen. Assume that the horizontal sweep is adjusted at 60 Hz. It is then producing 60 straight lines per second across the face of the CRT. The time for one sweep would be 1/60th of a second. Now a 60 Hz AC voltage is applied to the vertical input terminals. This wave starts at 0, rises to maximum positive, and returns to 0. It then increases to maximum negative and returns to 0. All of this occurs during one cycle. The period of this cycle is 1/60th of a second. Therefore, the horizontal sweep and the input signal voltage are synchronized. One wave appears on the screen. If horizontal sweep were set at 120 Hz, which is twice as fast as the 60 Hz input signal, then two complete waves would appear on the screen. The horizontal frequency can be adjusted so that the waveforms appear stationary or not moving. The display screen of a typical oscilloscope is a grid pattern. The grid pattern is used to aid the observer in measuring or comparing the wave pattern. See figure 10-32. A sine wave pattern is displayed on the grid. Using the grid and the setting of the vertical range selector switch, a voltage measurement can be made. The selector switch is used in conjunction with the grid to determine the voltage amplitude of the waveform. The grid is also used in conjunction with the time sweep setting of the scope. Voltage measurement. To measure the voltage of the wave displayed on the screen, simply use the grid as you would a common ruler. If the voltage selector switch, usually marked volts/divisor or div, or volt/centimeters, or cm, it is set on 0.2. Then the distance across each grid square from top to bottom is equal to 0.2 volts. If the volts divisor is set to 0.005, then the same grid space is equal to 5 millivolts. The small lines running up and down the center of the display are used to assist in making accurate measurements. The small lines divide each grid square into 5 equal parts. Look again at figure 10-32. The sine wave pattern covers a distance of 4 grid spaces from top to bottom. If the volts div selector switch is set to or set on 0.2, then the voltage amplitude of the waveform is equal to 0.8 volts peak to peak. A probe is used to connect the oscilloscope to the test circuit. A typical oscilloscope probe is shown in figure 10-33. It is constructed of shielded cable with a connector on one end and the probe tip on the other. The shielded cable is used to prevent interference from stray electromagnetic fields. Most probes are also equipped with a switch for amplifying the reading being taken. The two switch settings are usually marked X1 and X10, which means times 1 and times 10. When the slide switch on the probe is set at times 10, the voltage reading on the grid should be multiplied by 10. When the probe is equipped with a multiplier such as times 10, then the probe is referred to as an attenuator probe. The times 10 reading is due to an internal resistor that is connected in series with the probe lead. Time period and frequency. The time period for the wave can be determined in a similar fashion to that used for finding the voltage. The time period of the sweep is set using the time div selector switch. The time period selector switch is marked in whole seconds, milliseconds, and microseconds. If the time div selector switch is set at 0.1 milliseconds, then each grid space is equal to 0.1 millisecond. If the time div selector switch is set to 2 seconds, then each grid spacing is equal to 2 whole seconds. Look again at figure 10-32. The selector switch time div is set to 0.5 milliseconds. The sine wave pattern covers 4 grid spaces to complete 1 full cycle. The time period is equal to 0.002 seconds. To find the frequency of the wave, we divide 1 by the time period in each example, or in the example in figure 10-32. The frequency is equal to 500 Hz, or 1 divided 0.002, which is 500. Calibration. To ensure accurate readings are taken from the oscilloscope, it should be calibrated before use. The exact method of calibration will vary from scope to scope. The calibration technique described here is generic in nature and may not exactly match the scope you will be using. Always read the owner's manual to learn how to properly calibrate your oscilloscope. A square wave pattern is generally placed on the screen to calibrate the amplitude and the time period. The square wave can also be used to correct any distortion caused by the oscilloscope's probe. First, locate a point on the face of the oscilloscope, usually marked Cal. which is the abbreviation for calibration. This point is where you will connect the tip of the probe. The voltage, time period, and wave shape is provided by the scope as perfect reference for the calibration operation. A square wave will appear on the screen. From this point, the appropriate adjustments can be made to make the wave on the screen match the expected reference wave. Most scopes use 0.5 volts at 1000 Hz square wave as reference. See figure 10-34. The three examples of the square wave are shown. The rounded off or sharp peaked corners of the square wave patterns indicate that the probe needs adjustment. There's usually a small screw head in the side of the probe or at the connector. Adjust the screw until the square wave has a nice squared off corner appearance as indicated in frame on the left side of the figure 10-34. Intensity and focus. The focus and intensity control the appearance of the wave on the CRT screen. Focus is used to make the wave appear sharper. It eliminates any fuzzy appearance the wave may have. The intensity controls the brightness of the light beam striking the front of the screen. The intensity should never be set at a level higher than is needed to comfortably observe the wave pattern. If the setting of the intensity is too high and the scope is left unattended, the display screen can be permanently damaged. Reduce the intensity when you're not using the scope, before the scope is turned on and while it is warming up. The intensity should be set to its lowest setting. After the warm-up period, check the owner's manual for recommended warm-up time. It is safe to adjust the intensity level. Additional features. Today, many oscilloscopes in use are completely digital and incorporate a computer as a part of the scope system. The wave pattern can be observed as well as saved to a battery-powered computer memory. Many scopes are also equipped with print-to-paper capability to copy the form wave pattern. Some scopes used today are a combination of VOM and oscilloscope with a display screen. The display screen will not only display the wave pattern but also digitally display the frequency and voltage values. The oscilloscopes can also be connected directly to a personal computer. This is referred to as a data acquisition or transfer. This application usually requires an expansion card for the computer, software to run the program, and a interface cable to connect the oscilloscope to the computer. These peripherals are often provided with the scope. A personal computer used in this way will display the wave patterns, voltage, and frequency of the wave form. The information can be downloaded directly into documents for use in reports or training manuals. Review questions for section 10.5. Number 1, the oscilloscope is used to display what? Wave patterns. And what else? Voltages in the circuit are being tested. The X10 of an oscilloscope probe means that the reading on the screen is amplified by 10 times. 3. If the oscilloscope volts div setting is set to 0.2 and the wave shape covers 4 grid squares, what is the voltage? In this case, it is 0.8 volts. Before using an oscilloscope, you should calibrate it. Number 5, the height of the waveform is controlled by the volts div selector switch. Number 6, the number of cycles displayed on the CRT screen is controlled by the time div selector switch. The intensity is set to high If the intensity is set too high, the display screen could be damaged. Summary for this chapter, chapter 10. To produce an induced voltage, to produce an induced current with magnetism, three factors must exist. First, there must be a magnetic field. Second, there must be a conductor or coil in a closed circuit. Third, there must be a relative movement between the field and the conductor. 2. A generator is a device that converts mechanical energy into electrical energy. 3. Lenz Law states that the polarity of an induced EMF is such that it sets up a current, the magnetic field of which always opposes the change in the existing field. 4. Direct current, or DC, is current flowing in a single direction through a conductor. Alternating current, AC, is current flowing in more than one direction through a conductor. 5. Direct current generators have commutators, while AC generators or alternators have slip rings. Generator losses include copper losses, eddy currents, and hysteresis or hysteresis losses. These losses reduce their efficiency. 7. Generator types include the shunt, series, and compound generators. They can be independently excited or self-excited. 8. Regulation of a power source, whether it is generator or a power supply, can be defined as the percentage of voltage drop between no load and full load. 9. A cycle is a complete set of positive and negative values for alternating current. 10. Frequency is the number of cycles that occur each second. It is measured in hertz. 11. The value of AC that does actual work is referred to as the effective or root mean square value. 12. Formulas for converting the effective value to the peak value and vice versa are shown on the screen. Middle is E effective equals to 0.707 times E max, or E max equals to 1.414 times E effective. 13. Two sine waves are in phase when they are of the same frequency and they go through the 0 points at the same time. 14. The three-phase generator consists of a rotating magnetic field inside 3 sets of windings. 15. To connect generators in parallel, each generator's frequency, voltage, and instantaneous polarity must match. 16. Generators generally fail because of excessive brush wear, excessive bearing wear, and or electrical overload. 17. The oscilloscope is a test instrument that permits observation of waveforms in an electronic circuit. Lastly, 18. To ensure accurate readings are taken from the oscilloscope, it should be calibrated before use. Test your knowledge questions for this chapter. Number 1. The highest induced voltages are produced when the coils cut the magnetic fields at blank angles. That would be at right angles. Number 2. Commutators are used on blank current generators, and then slip rings are used on blank current generators. The answer is DC for the first, AC for the second. Commutators are used on DC current generators, and slip rings are used on AC current generators, also called alternators. Number 3, in what way can a pulsating current be improved? Generating several pulsating currents timed so that they fill in the wave voids. Number 4, what does the strength of the induced voltage depend on? And the answer for that is A, B, and C. A being the number of magnetic lines of force cut by the coil, B the size of the armature, and C the speed at which the conductor moves through the field. D is not correct. 5. State the mathematical equation used to find the strength of induced voltage in a rotating coil. That would be E equals theta times N divided by 10 to the 8th power. For that, see your text, page 141. Question 6. Losses resulting from resistance in the windings are classified as blank losses. That would be current squared times resistance, or I squared R losses, or power equals to I squared R. Number 7. An eddy current produces heat, B flows in the core of an armature winding, C causes a loss of energy, or D all of the above. D is the correct answer. 8. Explain the cause of hysteresis loss, and it is molecular friction and heat loss in the armature. Question 9. Identify each of the following generator diagrams. A is identified as a series wound, B is identified as a parallel or shunt wound generator, and C is a compound wound generator. Question 10. A generator has a no load voltage of 25 volts. When the load is applied, terminal voltage drops to 24 volts. What is the percent of the regulation? For this, we use the equation formula in the screen, where the percentage of regulation equals to voltage no load minus voltage full load divided by voltage efficient, and that is multiplied by 100 for the percentage. In this case is 25 minus 24 divided 24 times 100, which is 0.042 times 100, which is 4.220. That is the answer for number 10. Number 11. A generated voltage has a peak value of 240 volts. What is the instantaneous voltage at 60 degrees? For this, we use this formula where E, which is again the instantaneous voltage, that's why it's a lowercase e, equals to the voltage max times the sine of 60% or 60 degrees. Plug in the numbers, 240 times 0.866, and we get 207.84 volts. Question 12. What is the effective value of the generated voltage in problem 11? For this, we get the formula voltage efficient equals to 0.66 times voltage max. It's in this case 0.866 times 240 volt which is equal to 207.84 volts. Finally, question 13. Assume that a wall outlet in your home has an effective value of 117 volts. What is the peak value of the alternating current coming from that outlet? For this, we use the formula shown. Max equals to 1.144 or 1.414 times E efficient, which is 1.414 times 117 volts in this case, which is 165.43 volts. Motion simulators. The basic operation of pneumatic air or hydraulic liquid cylinders is quite simple. A pump is used to pump air or some hydraulic fluid into a tank to produce a constant supply of pressure. The release of air or hydraulic fluid pressure through the system can be controlled manually or through an electrical system. As a typical example, we shall examine an electrically controlled pneumatic system. When the circuit to solenoid A is completed, air is released into the cylinder. As the air pressure flows into the cylinder, the piston slides out. This action moves an object attached to the piston rod. When the solenoid is no longer in the open position, the cylinder stops. The piston rod and attached object will remain in position until the air pressure is released from the cylinder. Activating solenoid B releases the air pressure from inside the cylinder. The operational principle is very simple. Let's look at how these principles might be used in a flight simulator or an amusement park ride. An aircraft simulator usually consists of a cockpit, including all controls found in the actual aircraft model. The craft is mounted on a system of cylinders, such as those described above. The combined action of these cylinders can cause the aircraft to simulate left and right banks, climbs, dives, and even vibrations. The purpose of the simulator is to simulate flight conditions without requiring the pilot to leave the ground. This method is used to train pilots on both the basics of flight and on emergency conditions. The pilot can practice maneuvers over and over again without endangering himself or the general public. This type of training is also very cost effective or efficient. Simulators are used extensively by airline companies and the space industry. New virtual motion simulators are now being used in amusement rides and other simulations of motion, such as downhill skiing. The combination of cylinders with computer programs has caused the use of motion simulators to expand rapidly. This is experiment 10-1, building a generator. In this experiment, you will construct and test a simple generator. The materials needed would be one small motor, possibly from a toy automobile, one variable resistor, 0 to 500 ohms, one dual pole, dual throw switch, DP/DT switch, one multimeter, one galvanometer, and one roll of friction tape. Step 1 is to wrap the shaft of the small motor with friction tape. Step 2 is to assemble the circuit shown in Exhibit 10-1A. Use your meter to set the variable resistor to 100 ohms. When hooking the meter to the circuit, the multimeter should be set to read milliamps. Rotate the shaft on the small motor. Note the switch in the circuit allows you to take measurements of rotating in either the clockwise or counterclockwise direction. Make sure the switch is in a position to give you a positive reading. Finally, step 4, take the readings with the shaft rotating in both directions. If possible, take readings with the shaft rotating at different speeds. Then discuss your results. This is the end of chapter 10. Congratulations. You have completed this lesson. After you've finished all reviews, quizzes, tests, and experiments, you'll have earned this electronics course rank.